Hi folks, welcome to week 5, another week of KDD2. We are in the middle of lecture 2, high dimensional data, and we are not done yet, so we will talk about clustering in the remainder. So we talked about feature spaces in general. As you may recall, we also talked extensively about challenges facing when we want to deal or want to analyze high dimensional data. The curse of dimensionality, and then we came across some methods for typically supervised feature selection, where we try to find the suitable features for a given supervised task, typically getting rid of irrelevant features. So we got to know that for the curse of dimensionality, the big problem is first of all the irrelevant features, and second, also the redundant features, and we wanted to get rid of them. First, with feature selection methods, where we just try to evaluate each feature and its corresponding impact on, for example, the target value if you are in the supervised setting, and then just take a reduced number of features. But in feature selection, we keep the original features. And then we talked about feature reduction, sometimes also a little bit misleading, called metric learning. Metric learning, in fact, is also kind of different approach. But anyway, so feature reduction was not only the idea of removing or reducing the set of features we are working on, but also to come up with different ones. Yeah, so PCA was one of the things we came across here, where we derived new features with the assumption that the direction of highest variance is probably or possibly the direction which we want to, or which exhibits the patterns we are searching for. Yeah, so if it's a supervised setting, we assume that the variance or the directions of highest variance reveal the best direction, the best dimensions to distinguish between the classes, to build a classifier. And now we will talk about clustering, which is again unsupervised. Well, some of the methods we got to know here in subsection 4 were also unsupervised. So PCA, SVD, they are unsupervised in general, but we'll see that for many applications, at least, so there are applications where simply coming up with one global reduced feature space is not enough, and we'll talk about that in this subsection. And you see that the subsection is quite huge still. The amount of slides is still more than 2/3. So there are a lot of different approaches, because this is a huge branch of research, and an interesting one actually. And we'll talk about that extensively. So, but we will start off with challenges. What are the challenges for clustering? So we go back to this customer recommendation example, where customers rate products, for example, movies. And typically we have the rows where representing the customers, the objects, potentially millions, and we have the columns, which are the products, the features of our feature space, of our data space, which represents, so each column represents a product. And typically we have hundreds to thousands of them. Yeah, so this is a really huge data matrix. Of course, the rating of product I by user J is the value in the matrix, is the ith column, and the jth the ith row, and the jth column, of course. No? And now we want to do a customer segmentation, meaning we want to cluster the customers, we want to group cluster customers. So we want to find groups of persons, and what do they or what should they semantically give us? Well, those group of persons should be homogeneous in terms of their preferences or the disfavors for the products that they have rated. So, for example, movies. So they should like or dislike the same movies. Yeah, we want to find persons that share similar preferences or disfavors. And that can be, for example, used in or is actually used in personalized target marketing. So persons are or customers are segmented. So they are partitioned into interest groups, so to say, and then people are, I would say, attacked with marketing things that potentially fit better to them than if you just do it on the grünen Wiese, the green grass, so to say, yeah? Without any personalized grouping before. The challenge here is typically that customers may be grouped differently according to different preferences and disfavors, meaning according to different products or different subsets of products. And this reminds us to the baby shape game. Yeah. Now it's not well. The task is to find groups of persons. The features may be some, I don't know, science fiction movies is maybe one group corresponding to the shape in the baby shape game, and maybe another group of movies is romance, what we had just last week in the SVD example. So romance, maybe the other kind of semantic concept in the whole thing, which, for example, corresponds to the color in the baby shape game. And you see that the objects, the items, could be grouped differently according to these different concepts, and the same may be or is likely to be true for the customers. Yeah, so customers may be completely differently grouped according to their favor or disfavor in science fiction movies, and according to their preferences and disfavors in romance movies, and so on and so on. Yeah? So it's just because we may have different kind of semantically different concepts in the whole feature space. So that brings us again to the curse of dimensionality. Well, we had these relevant and irrelevant attributes. Well, for a given concept, of course, if we have a lot of features, and we are in the high dimensional data section, so if we have a lot of features, we may face the curse because of irrelevant attributes. Yeah, so not all features, but only a subset of the features may be relevant for the clustering. So here is an example. So if you take this two-dimensional space here, well, this partly forms a cluster, especially if we have some noise around here. But if you project all that stuff on this attribute here, you find out that those guys, those points here, have very, very similar values in this particular subspace, in this particular attribute feature, meaning that if you only consider this here, they may form a cluster. Yeah? We want to have clusters as a group of objects that are similar to each other. So if you project them on this axis here, on the x-axis, they are extremely similar to each other. So they are a kind of cluster. Yeah? On the other hand, if you project them on the y-axis, they are spread all over, so they do not really form a cluster in that particular feature or particular attribute. Yeah? So we have only one relevant feature. We will call that sometimes also a relevant subspace if we have a set of attributes, set of features, and there are irrelevant attributes. Yeah? And groups of similar points may be identified only when we consider those relevant features and disregard the irrelevant features. And to make the whole thing a little worse is, and now we are back in the baby shape game, different subsets of attributes may be relevant for different clusters. So we thought about this example of the baby shape game where we have 10 features, 5 features represent the shape of the items, 5 features represent the color of the items. So if we just concentrate on the 5 representing the color, we will end up in a completely different cluster if we rather than if we focus on just the other 5 features representing the shape. So different subsets of attributes may be relevant for different clusters. So what is the effect on clustering of the cursive dimensionality? Well, we know that if we have a lot of irrelevant attributes, then the traditional distance functions give equal weights to all dimensions. That means that the irrelevant attributes, if they are if we have too many of them, they just have a bias and they just overrule the relevant ones and somehow mask the patterns, because not all dimensions are of equal importance, but we give equal importance, equal weight to all the dimensions. So adding irrelevant attributes, dimensions, features obviously ruins any clustering based on distance functions, any clustering algorithm or result of clustering algorithms based on distance functions. Especially distance function that equally weights all dimensions. So one obvious solution is, of course, to upweight or downweight relevant and irrelevant attributes, but we will talk about finding relevant or irrelevant attributes because it's unsupervised, so you don't know what the relevant and irrelevant attributes are.